Okay, hi everybody. So, problem 26 I deleted because it's just reflecting my own struggles when I was a student. I didn't really understand what tangent was. I did not understand what arctangent was. And I guess it's just not part of this course. So if you're like me and you don't understand those things, just know that I also didn't understand it. Anyway, okay, so problem 26 is not a problem. Problem 27. Precisely define the meaning of the symbols this and this. Okay, so why don't I just do this one? So let's start with, let's actually do this one. A sub n goes to minus infinity. So this only makes sense if the a sub n are real numbers and the n is a natural number. In other words, we have a real valued sequence. This means we have a, sometimes people say real valued sequence because the values, a sequence is a function from the natural numbers to somewhere. And so if it's a function to the reals, we say it's real valued. If it's a function to the complex numbers, we say it's complex valued. And if it's a function to the rational numbers, then we say it would be rational valued. I don't know. Okay. Oops. There we go. Oops, and then I got rid of my Q. There we go. Okay, so now what does it mean to be... I can't take it like... I can't say like, here's negative infinity, let's put a ball of radius d around it. So that won't work. And because of that, I have to find a new way to say that something is close to infinity. So instead of choose d, a positive number, and then create a ball around infinity, that won't work. So instead, we will choose b for bound. How about any real number bound? And I guess really I need to emphasize for any. For any. So this symbol means that for any real number, there exists a cutoff value such that past that cutoff value, everything is close to, to negative infinity, so then the a sub n's would be less than b. Yeah. So I'm picturing like, if they're going to challenge me, they're going to choose a really negative b, like b equals negative 1 million. And I'll say, fine, no problem. There, if I go out, there exists some number that all the terms of the sequence are smaller than that. They're, all here. And then over here, there's only finitely many. So they're not all here, but infinitely many are here. And then only finitely many are here. And so since negative infinity is sort of like over there, this is our definition. So an to negative infinity means this. For any b, for any real number, there exists a cutoff that when you're past that cutoff, you're less than b. If that's true for any real number, then we say that the sequence goes to negative infinity, or diverges to negative infinity. Okay. Then you wouldn't be done. You'd also have to figure out what this means, but it's very similar. Okay, let's look at 28. Give an example of a sequence that is unbounded but does not diverge to infinity or negative infinity. So yeah, we did this in Perusall, so check Perusall for several examples. B, can you give such an example whose components are all positive? This is also in Perusall. Let me just say that one really quick. How about this sequence? Oh wait, they have to all be positive numbers. So 2, 1, 4, 1, 6, 1, 8, 1, 10, 1, 12, dot, 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 dot. In other words, a sub n equals n if n even, a sub n equals 1 if n odd. That defines a sequence. It's a map from there to there, I guess. And its elements are all positive numbers, yet, and it's unbounded, but it doesn't diverge to infinity, and it doesn't diverge to negative infinity. So that's 28b. Okay, 29. By the way, I'm going through these fast. I do not expect you to be able to understand these quickly. You need to like pause the video, find these examples in the book if they're there, or just think about them, and really just remind yourself, like, really most of the time is probably going to be spent about thinking about what is the question asking. That is where your main thinking will occur. What is the question even asking? That'll take time. You have to spend time thinking about it. Make sure that you know what these words mean. Diverge to infinity, diverge to negative infinity. That's those things right here. Yeah. Okay. 29. Problem 29. Give an example of a function where the associated sequence converges, but the function has no limit as x goes to infinity. Okay. So if you do like a wavy sine wave, here's a function. That's my function sine of x. X goes to sine of x. It's a real valued function. It's not a sequence. This is a real valued function, a map from the real numbers to the reals. And it has no limit because it keeps going up and down, up and down. So its limit's not 1, its limit's not -1, its limit's not 0. It's just bounces around. It has no limit. Has no limit. No limit when? As x goes to infinity. Okay. But if you just pick out all the values that are 0, then you just get a constant sequence. So what sequence is that? Send the natural number n to a real number. What real number? So see that no matter what integer you put in here, you will get 0. This is just 0. So the sequence is just 0 for all inputs. It's just identically 0. It's a constant sequence. Constant sequences converge to their constant value. Okay. So the associated sequence does converge. Let's look at 30. What is the precise definition of the symbols blah, 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 blah equals L for a real valued function like that and a real number L? Okay, so this is one of those things that you just need to find it in our textbook and just memorize it. Just think about it. Okay, I always say memorize, but what I mean is like commit it to a story in your mind. It should be connected to pictures. It should be connected to words. It should be connected to intuition. This should take on some sort of meaning in your mind so that if somebody says, what does this mean precisely? In about 1 minute, you will be able to reconstruct the precise definition of these symbols. Okay? That's what I mean by memorize. It's maybe memorize is a bad word for this. But anyway. Okay, and then this proof is, I don't know if this proof is in your book, so why don't I prove it? Prove that this limit implies that the associated sequence converges. Okay, so we are going to assume this and prove this to L. So what am I doing? So now I'm just quizzing myself. Do I even remember what did the question ask me to do? Can I remember it? That's a great quiz for yourself. You're certainly not going to be able to solve the problem if you can't even remember what the problem is asking without looking. Okay, so let me think. I think it's saying for me to assume that this is true. I'll finish this and prove that if I define a sequence as just f, just plug in the integer into f, then that sequence converges to L. Okay, so how do I prove this? How do I prove that? Well, every time we prove convergence, we start by saying choose a positive number, find a capital N such that past that cutoff implies that an minus L is less than D. That's what we need to do. Our proof starts, for any convergence, it starts the same way every time. Okay, so choose this D. Now, how the heck are we going to find this capital N? Well, we have to use what we assumed to be true. Our assumption is that this holds. Okay, well then that means that if I choose this D, we know by star, let's call this star up here. We know by star, because we assumed that star is true, there exists some n tilde. I'm just making up a new name. I could call it m. How about m? There exists m, a real number, such that the real number x past m implies f of x is that close to, is d close to L. Okay, that is what we know by assuming star and the fact that I know what these symbols mean. And I'm quick with them, it's fast for me. I've really absorbed what these symbols mean and their precise definition. Okay, well this is easy. Okay, so take n to be the next integer after capital M. The next integer after capital M. Okay, so like if capital M was 104,052.3, then take n to be 1,453. Okay, this is example. I don't know what EG means, but I've seen people use it for like for example. So why don't I just write for example if m was that, n is that. Okay, then n greater than or equal to n is greater than or equal to n, so that f of n minus L is less than D. But f of n is our sequence. And that's what we wanted to prove, that a sub n minus L is less than D. And f of n is a sub n. So we're good. So we used this to prove this. Okay, so this thing, assuming that true, told us that there does exist some capital M, and then we used capital M to give us a capital N, and then we got what we needed, which was this thing right here. Okay. That's all done. So then I get to color a box.